Okay, should we get started? So, glad to finally meet you. I'm Vishnu. I'm the course instructor for the second half of this course. You may have seen me on YouTube. So, I'd like some feedback on how this is going. Is this teaching style at all effective, or what do you guys think? Yeah.
Okay, I probably disagree with most of it, but in all format, personally, I think that I prefer actual lectures because I don't think I'm handling the responsibility of doing this at my own time very well. I tend to push it off, and also it's easier for me to ask questions in person and get solutions right then and there if I have an issue with something in the content.
Okay. Other thoughts?
So, when I emailed you, I said I'd try to get some feedback from everyone. So, the majority of the people said they really prefer the online lectures because they can more or less work at their own pace. So, if they maybe getting a bit, days out, or whatever, they can pause the video, they can take a break or whatever. And also, the free Monday slot does help with catching up with other work, whereas you can prolong this. You can watch 30 minutes a day and be done in 4 days. And you can get a better understanding because you can short stints rather than a full 2-hour lecture where you can lose attention span very easy. So majority of the people do enjoy the online lectures, but one person does like coming into lectures. It's literally
Okay. Other opinions? I'm perfectly happy to change things up if it's not productive, and I'm not trying to get away with not doing any work here. So I realize that my role is to teach you. It's just that I had to be away, and this was the solution I came up with while I was away. There's some literature in education that suggests this so-called flipped classroom is an effective way of teaching. But most of these studies are with humanities courses or in history courses rather than in physics courses. And a lot of these education people, they don't understand statistics at all. So they have small sample sizes, they extrapolate patterns from very limited data. And these journals are really journals of behavior of North American college students, rather than college students internationally, or your experience in academia differs greatly from the experience of the people from which these studies are based. So it's not clear whether any of these methodologies is actually functional and workable, but it is the new trend in higher education to give you more independence by focusing lecture classes on problem solving rather than on presenting material, and having you process material on your own. This, as was mentioned, if you have the ability to pause the video, this lets you process things in smaller chunks. And there's also been some studies that the most efficient way to process materials in 10-minute chunks rather than in hour, 2-hour lecture periods. So, this literature is very mixed, and as I said, it's not clear whether it's applicable to physics or mathematics or areas like this. So, I'm happy to keep doing things this way. I'm also happy to come in and teach for 2 hours. We've had a few opinions so far. What do the rest of you think? I'd like to hear feedback from more than just 1 or 2 people.
I think once you have your online video, you can come across anything that's difficult to understand and conceptualize. Leave a link in the description below on YouTube on the video. So in a certain minute, let's say if you're on the 14th minute, you discuss something very difficult, leave a link in the description below and be like, okay, this concept is discussed on the 14th minute. So we can pause the video then and go check out that.
Well, okay, that's kind of hard to do because I need to watch the video multiple times myself. And watching yourself giving a lecture is not particularly edifying for a lecturer. You always stumble on things you would have done better, or you could have done. No, myself watching these videos, it's a very weird experience. In that it's also very weird giving a lecture to an empty room, because you don't get visual feedback from the audience as to whether things are being understood or not. It's hard to do humor to an empty classroom as well, so the lectures aren't very funny. And I try to do humor occasionally. I usually fail, but the attempt's worthwhile. Even the attempt is difficult in an empty room. So I appreciate their issues, but it may be worth noting that there are certain things that are difficult, and those things you should focus on, and maybe I can do better at pointing those things out. So I appreciate that comment. Yeah.
I personally much prefer the video lectures because, like people say, it lets you work at your own pace. If you want to speed up the video, you can. If you want to slow it down, you can. It also really helps make tests and tutorials approach. Because sometimes your class notes won't be perfect because you're in the lecture then you're in a rush and you're trying to shorthand. But you can now revisit the lectures on those specific sections of that specific thing and watch it again to reaffirm your understanding and see how it applies specifically to that question, which I feel really helps.
So the lectures aren't intended to be complete, especially not in the video recording, in the sense that they're to point out, they're like a table of contents maybe, they're a guide. They're not really comprehensive in the way that a textbook would be comprehensive. Sort of a distillation of the textbook to key points, and if there are confusions, I would suggest revisiting the textbook to address those confusions, because I'm stating results sometimes, not deriving things step by step. And a lot of physics understanding, you need to go through it step by step. So I appreciate that you can stop things and process things slower, and that's definitely a good thing. But you shouldn't think about the videos as being a complete thing in itself. And in fact, my feeling is that the best way to learn is just by working problems independent of lectures. And you read and you process the stuff you need to work out interesting problems, and that way you learn stuff. That's how I learned personally, just by working out a bunch of problems, independent of lectures. When I was a student, I didn't attend my lectures very often because it's much easier to just do the problems and learn that way. Different people do it in different ways. Other comments? Yeah.
I also think that if we were, because you sort of release one every week, so it gives us, instead of just say this double period could more or less cover an entire lecture if it's an hour and a half, we've got the entire week to work through all of that compared to the textbook, as well as look at the problems in the textbook and stuff. So it gives us a lot more, I don't want to say free time, but a lot more time to actually work on problems as opposed to completely just taking the notes in the class.
Okay. Others? So I think what we may do is we may just continue doing the videos, but I'll also make myself available to answer questions in class. And maybe that's sort of a compromise position in which we can do the videos, but also have a more immediate chance to get feedback rather than having people email me or whatever. So let's see how that goes. And how are the problems coming along? Are you guys able to address the problems? We've had dark matter, we've had CMB, we've had Big Bang nucleus so far. I've released problem sets for all three of these. What's your take on how prepared you are to tackle the problems? Because in the end, physics is computational science. It's wonderful to talk. It's wonderful to present structures, but you actually have to work problems in order to understand what's going on. And in fact, there's some problems that are going to be papers or were papers in the past that really develop the subject and present research and bring research into a modern form where it's a body of knowledge rather than stuff that's being discovered constantly. In cosmology, it's sort of a weird subject because in the past 10 years, past 20 years, our conception of the universe has radically changed. And this is because of data. We have these telescopes up in the sky that are observing things, and these observations are recasting our view of the universe, essentially in real time. One of the great puzzles that's perplexing professional cosmologists today is if you measure the Hubble parameter at small redshift and large redshift, you get different answers. And no one knows why. If you take CMB measurements, which are reflective of the universe in a very early time, therefore high redshift, you get one answer. And if you take supernova measurements, which are reflective of the universe at a much more modern time period, a few billion years ago as opposed to 13 billion years ago, you get a different value of the Hubble parameter. And these values, they differ by 4 sigma. So it's almost significant enough to be a discovery. And no one knows why. No one knows why these 2 different measurements of the Hubble parameter give us different numbers. And this mystery has emerged in the last year or 2. So the subject is again changing before our eyes. And we also have the opportunity to contribute to these discoveries and figure out what's going on. So it's a wonderful time to be doing cosmology. The point I was making, though, is that in doing the problems, you're confronting these sort of issues, and you're challenging what you understand and what you don't understand, and hopefully clarifying those confusions. So, in order to understand the subject, you need to be able to work problems in the subject. I'm wondering how that's going.
Talk about the TATs.
Yeah.
Okay. So, TAT 5 was due on Monday, so we haven't really had much time to go through all this. So, I don't know what other people, I don't know if they may have been going through all the TATs, but I just think a lot of past TATs.
Okay.
I think that's
So let's focus then on problem solving. Let's spend some time today and maybe early next week discussing problems on dark matter and CMB and seeing how we understand those problems. Yeah.
Also keep in mind having these every weekly session where you can.
I can't hear. Could you speak up a little?
I'm saying can we keep in mind that we can have a weekly session for Thursdays and Fridays for this to 9 to 9:25 to make sure that we're all on the same page. The same way we have been with us before we do this class and like we say on Monday, we just need to class pretty much that. If we keep like weekly, if we do the videos all week, then we keep a weekly in-person session for us to ask those questions and keep up to date.
Exactly. So my plan, I think, is that I'll release the videos probably on Fridays. I haven't recorded videos for inflation yet, but I'll do that soon. And we'll meet at least once or twice a week in order to address any confusions you may have firsthand and also to discuss the problems. Okay.
Which is like at the conscious phrases that's having that free Monday and having the videos posted once a month and not very free so that we can have more free time to work with that's a switch.
Yes, that's the plan. You happy with the plan? Okay. Okay, so let me address confusions then. So far, we've discussed many different topics. Were there reports where I wasn't clear or you aren't clear on what's going on? What are the questions? And if you have other questions on cosmology, please feel free to ask. This is the most beautiful subject there is. We're studying the structure of the universe. There's nothing more exciting than this in all of physics. We're figuring out what happened at the Big Bang and everything that happened subsequent to the Big Bang in one cohesive coherent story. This is as fun as physics gets at some level because we're answering the deep questions, or trying to answer the deep questions. So what are the questions?
So one of the things that also is going through the cosmic microwave background is so when we start as x is equal to NQ in paradox, the derivation from that doesn't really make sense. So are we just defining things like gamma and what x and z and everything are, or what do they actually mean? That's what I don't really get.
Okay, so let me look at my notes and let me ask, where exactly are you? What exactly are you referring to?
So this is after loss scattering
Okay.
in the cosmic background dimension.
Just after the definition of capital X. Just after the definition of capital X.
No, so this is just after we got introduced to a combination of photonic coupling and loss scattering. And then after that we got the two barriers for all hydrogen. So after that.
Okay, so let me sort of describe what's happening. Initially, things are very hot and very dense. So what this means is that photons interacting with electrons and with atoms and so on. So as a result, you don't travel very far as a photon without bumping into something. And you usually have enough energy, but there's enough photons with sufficient energy to ionize hydrogen when you bump into a hydrogen atom, say. So the universe isn't transparent. It's opaque at this phase in its history. So how do you measure when the universe becomes transparent? That's sort of the first question to address. When did the left light moment actually happen? So the way we measure this is we define the mean free path of a photon. The mean free path is the average length of time you travel before you bump into something. So if you're drunk at home, it's how long you wander around aimlessly until you bounce into a piece of furniture. That distance is the mean free path at some level. That's what the photons are doing. They're just bouncing around between these atoms. Now, if you ask how often these photons bump into something in order for the universe to still remain opaque, it's a few times a week. So it's not like it's happening constantly. It's happening sufficiently that things are getting ionized in the process. So the way you measure when things become transparent is when the mean free path corresponds to the Hubble distance. So if you travel the Hubble distance before interacting with something, you're traveling essentially infinitely before you interact with something. So you're comparing the mean free path, gamma, to the Hubble parameter h. So how do you compute these things? Well, the Hubble parameter is a dot over a. So a dot over a has units. It's 1 over time is units of a dot over a. So you construct some object with units of 1 over time. That's gamma. Now, essentially, this is just dimensional analysis. Essentially, any calculation you want to do, if you're clever, you can get the answer by dimensional analysis. And the rest is just figuring out the factor in front. So what do we have here? We've got photons. Photons have a wavelength. The wavelength is a distance. Photons also travel at the speed of light. So that's a distance per time. We want something which is 1 over time. So the natural thing to do is take the speed of light and divide by the wavelength. This gives you something with units of frequency, 1 over time. So the rate at which photons scatter is going to be c divided by lambda. Okay, so lambda is the mean free path of the photons. It's a natural thing with units of distance. So we can compute this. We have gamma is c over lambda. Lambda is the mean free path. And we want to express this in terms of what's hanging around. So there's what's lambda? Well, how do you determine what lambda is? This is basically how long you can go before you interact with something. So there's a density of stuff that's around. Number density of stuff is number density of electrons, say. This is the number of electrons per volume. So units of this guy is a volume. So in order to make this a length, you need to multiply by an area here. So the national area is the cross-section for the interactions. So that's sigma e. So this gives us something with units of length. And you're taking c over lambda then, you have ne sigma e times c. And this gives us gamma, which we compare to the Hubble parameter. So if gamma is bigger than the Hubble parameter, then you're effectively transparent. If gamma is smaller than the Hubble parameter, you're effectively opaque. That's where these things come from. Did I answer your question, or did I answer a different question?
And I have another one.
Yeah, okay.
So when you drew the circle with, when you're explaining loss scattering, I didn't
Yeah.
quite understand what loss scattering means.
Okay, so we have the horizon. But we can't see up to the horizon because the universe was at one point opaque. So there's this shell here, which we can't access directly. We can access as a boundary of this shell. The boundary of this shell is the CME. So we're here in the middle. We're getting photons from all directions. But the photons we're seeing are the earliest photons that we're able to have an infinite mean-free path. So these are the photons such that their mean-free path exceeds the Hubble parameter. The first photons for which this happens. So at some point, each of these photons will have interacted with an electron before it had an infinite mean-free path. That's the last scattering. The last time it interacted with an electron is its last scattering. So we're seeing the surface of last scattering in the sense these are the photons after they've had their final interaction.
But since like the universe is now transparent, we shouldn't have the shell anymore, should we?
The shell is sort of a remnant of when the universe wasn't transparent. So remember, as you're looking out into space, you're looking backward in time because the speed of light is finite. So if you look back as far as you possibly can, you encounter these particular photons. They're the first photons you can see. Okay? And they date back to the universe that's 380,000 years old. So the last scattering surface is a bit of a misnomer in that it's really a last scattering shell in that a particular photon, it might have interacted at redshift z equals 1200 say. But another photon may have interacted at redshift z equals 1180. That's also possible. So there's some range of redshifts for these photons. So it's really a last scattering shell for these photons. And this is very crucial because it tells us the universe when it was very young. And small fluctuations in the universe when it's very young are what leads to structures today. So we're getting a map of the universe at a very early time. And if we look at the universe at a much later time, we're seeing large-scale structures, for example, galaxies, superclusters, whatnot. Those structures arose from small fluctuations in the earlier epochs. Other questions? Yes?
When you were examining the temperature fluctuations in the CME, I think you got the angular diameter distance to like 30 megaparsecs.
Yeah, something like that.
But then when you worked out the physical size of the object on the surface of the glass gathering, I think you computed that as 1,300 megaparsecs. So I don't understand that.
Okay, let's see. Okay, so again, I don't remember the exact formula, we can work it out. So we have the angular diameter distance. This is, we'll call it dA, and this is related to the size of the object and what part of the sky it subtends. Okay? So dA is a distance, so it has to be related to the size of the object we're studying. And the angle is probably the denominator, delta theta. So this is dimensionless. So dimensions on the left-hand side and the right-hand side are both distances. Now, this guy here is the angular diameter distance. And L would be the size of the object at the surface of glass scattering. And delta theta is the part of the sky it covers. Okay, so essentially by dimensional analysis, that has to be what the formula is. Okay, so now we want to look at the early universe, the CMB. So we look at, I think it was 1100 was the redshift roughly. We know that the angular diameter distance is related to the horizon distance today divided by 1 plus z. I think it's 1 plus z. But you don't really care about the 1 plus z because this number is much, much bigger than 1. So dividing by 1100 divided by 1101 makes no difference at all. So we'll just call it z. Call it z last scattering. And the horizon distance today, that's model dependent. You can work this out in the benchmark model. And when you work it out in the benchmark model, this works out to 14,000 megaparsecs divided by 1100, which is the redshift. So when you divide these things together, you get 13 megaparsecs, which is the number I quoted in the lecture. Okay. So that's where the number comes from. Did I answer your question? Or?
No, when you compute the physical size of the object,
Yes.
this way I get a little more confused because I multiply the angular diameter.
Right, so we just rearrange this equation to have L is dA delta theta. Now, dA, we computed, was 13 megaparsecs. And the delta theta is measured in radians. Okay? So we find that for certain interesting structures, delta theta is about 7 degrees. So you convert this formula to degrees instead of radians. This is 0.22 megaparsecs delta theta per degree. So you plug in 7 degrees for delta theta, and you find that certain structures are corresponding to 1.6 megaparsecs.
That clarifies it because I don't know if I'm mistaken in the video you were talking about 13 megaparsecs to 13 megaparsecs.
Okay, maybe I made a mistake in the video. It's quite possible. But I think this is the calculation. One second. questions? Yeah.
I'd like to ask a question. So when you're deriving the impact parameters in the dark matter section,
Yeah.
for the gravitational lensing, I was a bit surprised with the dimensional analysis with the use of the Planck scale.
Okay.
I guess I'm not surprised that it worked, but I was just looking like what would be the physical motivation of introducing those scales
Okay, so
into that kind of problem.
right. So the logic there is that okay, so where's my eraser? I can already get this. Okay. Should be somewhere. Okay, I've got the eraser in my office. Okay, so the logic here is that we have some mass m, and we have some light that's traveling along, and it normally would just travel like that. Because of the presence of the mass, the light gets bent, and it curves around this mass. That's the lensing effect. So if you're an observer way out here, you'd extrapolate a light ray as coming from this direction, rather than when we're here. So we've got the mass m, we've got a distance b, the impact parameter, the distance of closest approach. And we want to measure how much light's been deflected. Okay? So you can do this calculation in general relativity. In the tutorial questions, this is one of the calculations you'll in fact do. I'll give you the geodesic equation. So light travels on geodesics. I'll tell you the equation that light follows, and then you'll work out what the actual angle of deflection is. But it turns out that just by knowing dimensions of things, you can get the answer up to a factor of 4 just by staring at the problem. And in fact, when physicists work in practice as theoretical physicists, for a calculation like this, it's enough in many cases to just know how it will behave rather than the actual answer up to a factor of 4. So it's sufficient to just puzzle out how this has to behave. Now, what do we know about this behavior? We know this is a general relativity effect. We know that the verification experimentally of general relativity was that Eddington went out and observed an eclipse, and during the eclipse he measured the deflection of the angle of the sunlight, of the starlight by the sun. So that was the experimental confirmation that this effect is a real physical effect. So it's a GR effect. The GR absorbs special relativity. So locally, special relativity is the applicable thing in GR. So we know that the speed of light will enter our answer. We also know, because it's general relativity, the strength of gravity will determine how much you get deflected. So we expect our answer to also involve u Newton. Light is a quantum thing, so it cares about h bar. But this particular calculation shouldn't care about h bar because it's purely a general relativity effect. Okay, so we know that c and g Newton should be there, but h bar shouldn't be there. So it's a fact that we know. We also know that as m gets bigger, theta better get bigger. So a massive object will deflect light more than a less massive object. So that's a fact. Then another fact is that if b gets huge, you're very, very far away from the mass. So in the limit where b gets large, delta theta should go to 0. Okay? So those are the facts that we know just by staring at the problem. Now, theta is dimensionless, while b and m have dimensions. B is a length, m is a mass. So I want to construct theta as a function of dimensionless parameters, which we'll call mu and rho. Okay? So how do I construct something dimensionless out of m? M's got a mass. So the natural thing to do is to divide by some other mass in order to get something which is dimensionless. What's the only mass that you can think of that involves these parameters c, g, Newton, and h bar? Well, Planck mass. So you divide by m Planck. Similarly, you're looking at rho as a distance, you divide by L Planck. So these are now dimensionless objects. So in principle, theta is a function of m, of mu, and rho independently. Okay, that's so far what we've derived. But we know that h bar has to drop out. So you do a combination of mu and rho such that h bar drops out. So m Planck is going to be, so you get m square root g Newton over square root h bar c here. And here you get b square root c cubed over square root g Newton h bar. So you have 1 over square root h bar in the denominator of both these expressions. So you just divide to get rid of that h bar. So the combination then is going to be x, which is the ratio of mu and rho. And this is m times g Newton divided by b c squared. You can tell it's ratio of dimensionless things. So x is itself dimensionless. So whatever answer you want is going to be some function of x. And you can think about this as a Taylor series in x. So it's going to be a0 plus a1 times x plus a2 times x squared plus blah, blah, blah. So if the mass wasn't there, the deflection would be 0. So we set a0 equal to 0. And we just have some coefficient times x. And we think about these effects as being subleading. So indeed, The mass is the numerator here. So as m gets bigger, the deflection gets bigger. B is the denominator. So as B gets huge, the angle of deflection gets to 0. So it's got the right scalar. G Newton's also in the numerator. So as you make gravity stronger, the deflection will get larger. So this has to be the right answer. And in fact, it's the right answer up to a factor of 4. So without knowing any general relativity, we're able to get the answer almost right. Yeah.
So I was going to ask if you're going to give us a formulation of the exam or the test.
Okay, so we should talk about the test, the exam. What exactly do you want?
No.
No, because like once we go through our notes, we find out there's a lot of formulas. And
I'm happy to have open note, open book, whatever.
That's perfect.
I'm happy you take home exam too. I'm not sure whether it's allowed by the rules, but would you like that?
Take the exam. No, why not?
Why not?
Democracy.
I like to come here.
It's just like I like intellectual democracy.
Oh yeah, take home music.
I actually don't know whether it's allowed, so let me check whether it is or it isn't.
If it is, yes. I think we'd like it if it is. But if it's not, then we can't do it.
I'm happy to give a definite time as well, and I'm not pressuring you to finish in 2 hours or whatever.
I think, because our physics lecturers would also like to give us a definite time, but since fees are small, there's all sorts of security guards and people there, so you can't go past the allotted time. So that's unfortunate.
Now, but so far, tests have been
I test that bit, but your exams you can't because you can't run your own exams. That's
Okay.
been invigilate. Yeah.
so do you have a time for the test, like around a specific date in mind?
because we have a
I think there is a time that's been set. I don't know what the time is offhand. It's been decided by.
We just have the exam.
There's a table somewhere you can look up for the exam time for every exam. It's on that
And you
table.
thought we had a second, like, class test, but we didn't, I don't think.
No, there's not going to be a second test.
Will the scope of the exam be everything or everything
Yes.
since the first?
It's everything. But the concentration will be on what's happening in the second half of the course, rather than the first half. But in principle, everything is covered. So everything in the history of the universe, from the Big Bang until the distant future, is fair game for you to be tested on. Yeah.
So considering those questions in the task, we had to derive the, I think it's the angle of deflection.
Yeah.
So when we have to introduce the Planck scales for mass and for the length, we introduce them after we consider dr over d small and or
No, what you're doing there is something different. So here I just used dimensional analysis to guess the answer. There you're actually calculating it. There's no M Planck and L Planck insertions there. You're doing a calculation. The point of the calculation is you're deriving, so the answer is going to be theta equals 4x. You're deriving the 4.
So you've already been given the equations that you need. You just need to manipulate the way that says the question. And you know in the tablets.
Yeah.
having a couple of my quick background. What was the reason for calculating tau of Z?
What is tau of f?
Tau of Z, when we calculated it, it's the integral from t to t naught of dt bar down to t bar. I think the optical depth, yeah. I don't get what the point was behind that.
Okay, this was in the CMB section. Okay. see. Okay, I think the logic there is that the optical depth is sort of a measure of how opaque the universe was. So the idea is that, okay, so we observe a CMB photon. When we observe a CMB photon, that photon will have been traveling ever since it last scattered on something. Okay? So let's consider the time interval t to t plus dt. So on this interval, what's the probability of this photon interacting with something? Okay, so the probability there is gamma of t, the rate of scattering, times dt. So we know that probability is dimensionless. It has to be proportional to rate of scattering. Rate of scattering is per time. So you multiply by delta t, since we've got this interval delta t, it's dimensionless. So it has to be that way. Okay, so if we think about tau of t is essentially the interval of this probability. It's the likelihood of scattering for a particular photon. So this guy is integral dt gamma of t. I'm integrating this from the time that it last scattered on something to when you observe it. So you observe it today. So the interval is from t to t0. Okay. So this dimensionless number tau is the optical depth. And what it describes is the expected number of scatterings for that photon. Okay? That's what the probability is measuring there. So that's sort of compute the optical depth. Yeah?
Just to get more understanding of like what cosmologists mean in terms of like, the map of the cosmic macro background is completely homogeneous. When I first looked at it, I never like doesn't instinctively think that's homogeneous, like you can clearly see the.
Okay, so there are multiple comments there. Let me make a few of them. First comment is that it's not totally homogeneous. There are small inhomogeneities. These small inhomogeneities have a meaning. They're not accidental, and they describe certain physics in the early universe. So, firstly, if you just take a measurement of the cosmic microwave background, and you ask what is the temperature of the sky at a particular point, so you point your telescope at some angle theta and phi, and you measure the temperature there. That temperature is going to be 2.73 Kelvin, roughly. But there's a small error associated to that. depending upon which angle you point your sky, you get a slightly different temperature. Okay? That difference between the temperature over there and the temperature over there is really tiny. It's 1 part in 10 to the 4th, or 1 part in 10 to the 5th. It's a very tiny difference in temperature between the sky here and the sky over there. Now, so if you plot the black body spectrum, if you plot all the photons from some part of the sky, and you plot what temperature those photons are at, what frequency you have, or what energy you have, you find it follows the Planck distribution really, really well. And peak, the Planck distribution is given to you by the temperature of the sky, the temperature of the CMB. Okay? So we know this temperature, we measure this temperature at different angles of the sky, we get the same answer, roughly. There are very tiny differences, and those are the inhomogeneities. Now, what do these inhomogeneities mean? How do these differences arise? It's a very deep question. It teaches us a lot about the structure of the universe when we're making this measurement, when the universe is 380,000 years old. Firstly, there's another mystery here, which we'll address next week when we discuss inflation. But if you think about as far that way in the universe as you can possibly see, and as far that way in the universe as you can possibly see, light from that end of the universe could not have reached that end of the universe within the lifetime of the universe. They're just at different parts of the sky. They're twice the horizon distance, right? The light we're seeing from over here has been traveling since 380,000 years. Light from over there has also been traveling since 380,000 years. It's just not possible for that part of the sky to receive light from over there. However, the temperatures are the same. How do the temperatures know to be the same when these different parts of the sky are not in causal communication? That's a mystery. That mystery is answered by this phenomenon called inflation, which says secretly those two different parts of the sky were in causal contact very early on. And they know to be the same temperature because they were causally connected in the early history of the universe. So the fact that the measurement of the temperature is the same everywhere leads us to certain conclusions about the structure of the universe at early times. Now, let's address these temperature fluctuations in the CMB. Where do they come from? Well, they come from the distribution of dark matter, basically. The distribution of dark matter was overdense in some places and underdense in some places. And because of these small density fluctuations in the dark matter, some photons travel out of a potential well, some photons travel through a potential well. And they redshift or blue shift depending upon whether they're going into the potential well or out of the potential well. Those tiny redshifts and blue shifts are what's responsible for the slight temperature fluctuations. So local density of dark matter, when the universe is 380,000 years old, is captured by these tiny fluctuations in the CMB.
So how do we say that the map turns out like green in some parts, bluish in some parts, just because of the sensitivity of the equipment, that it's not really much of a change in?
No, it's not sensitivity of the equipment. It's the fact that there were slight density fluctuations in the early universe. So if you have slightly overdense dark matter, then if gravity is stronger, but the dark matter is slightly overdense. So the photon that's leaving this area where there's an overdensity, it has to go up a potential well. It loses energy as it goes up a potential well. So it's going to be slightly colder than a photon that didn't have to do that. So it's a slight temperature fluctuation as a result of the density of dark matter. Okay, so the map of these fluctuations measures the dark matter distribution when the universe is 380,000 years old. And we know the dark matter clusters around galaxies. So it gives us a map as to where the galaxies will form when the universe is 380,000 years old.
So essentially, besides the gravitational effects of dark matter, you can also prove dark matter through those fluctuations of the CMB?
We infer the existence of dark matter through fluctuations in the CMB. Absolutely. Yeah.
You were saying the problem that the equation solved about different parts of the universe, like the shell being causally connected. How should this part know that the temperature should be the same? What do you mean, like this part should know that the temperature should be the same? Because it makes sense to me that if the Big Bang happened and we have radius in every direction, then the temperature should be the same as it expanded with the formula.
Okay, so the let's defer discussion of this until I give my inflation lectures. Let's revisit this in a bit. I will answer that question precisely. Let me do this in a more structured sort of way than sort of just improvising an answer. But yes, it's true that the Big Bang happened everywhere, and the remnants of the Big Bang are captured by things like the CMB. And it's true that different parts of the sky are the same temperature, even though different parts of the sky naively look to be causally disconnected. And that needs to be explained. What else?
So were we supposed to be handing out cuts for books?
I don't know. What do you think?
Probably.
I mean, when do you want to hand them in? I mean, what's your schedule like, and when do you think it's reasonable? And you just you did number 5, right?
Yes.
And is number 5 at the end of Dr. Beck's tutorials?
It's multi-component.
Okay, so I guess I numbered things incorrectly. My first, yeah.
Because the first chapter is pretty much like nothing. So type 1 was on chapter 2, type 2 is on chapter 3.
Okay, so I have tutorial 7, 8, and 9, it looks like. So I skipped tutorial 6. That's fine. You'll get perfects on tutorial 6. So tutorial 7, I think we can hand in be next Friday as a dark matter tutorial. Is a week reasonable? Okay, let's do that. And then subsequent tutorials will be due following Fridays. Okay, so I guess I'll put lectures up probably early next week for the inflation, and then we can start going over problems for all of these things. Okay, so I guess one thing to briefly look at then is tutorial 7, I called it, the dark matter tutorial. Just maybe look over those questions now and just read through the questions and let me know right now in real time whether the questions are straightforward or understandable or confusing or anything like that. Is it clear what I'm asking for? Is it sort of vaguely clear how to approach these questions? Yeah.
I had a question. How would you determine the mass density within a halo?
You measure it basically. It's not something you derive a priori. You take observations of how fast things are rotating, and because you know that the centripetal force law describes how fast things should be rotating as a classical approximation, you can tell how much mass is making these things rotate at the speeds they're rotating.
So you first need to look at the precision velocities of objects within that halo.
That's right. You know that the Newtonian central potential, the mass inside some spherical shell determines motion along the surface of that spherical shell. So by measuring different velocities at different distances, you're able to determine how much mass is there interior to that distance.
So getting the potential and proving that it's independent of it, how would you go about that? Because I know that you showed that V of R is independent of R, so I'm confused now.
Okay, so when V of R is independent, that means that V of R is constant, right? It's independent of R. So you need to come up with some way of calculating the masses there in order that V of R is independent of R. We know that the curve essentially flatlines, right? Because there's some phase where it looks like this. So the velocity is constant. That tells you something about the mass distribution. And we discussed certain theorems involving mass distributions. Yeah.
So with the alpha that you introduced when you were talking about Coma Galaxy cluster, I just wanted to know how does that happen that it's like you can work that out for just a specific galaxy without using alpha, but then for the galaxy cluster that's related by alpha.
So what you do is you make measurements, and you work out, based on those measurements, what alpha is for that particular galaxy. I think for Coma it worked out to be 0.4 or something. For other galaxies, it'll work out to be slightly different. If you just make these measurements. It's an empirical thing you're doing in computing alpha. It turns out that for almost all galaxies, alpha is around 0.4. And that tells us something about dark matter at some level. Because alpha is really a measurement of some effective potential involving the dark matter.
So would that say, like, when you were talking about the potential walls that dark matter has when you think of it not being constant, does that show that dark matter actually could be something smooth and not contained as walls?
That's in a slightly different context. So when we're talking about potential wells and so on, that was in the CMB time frame. So that these were, dark matter distributions when the universe is around 80,000 years old. It describes, these temperature fluctuations we were seeing in the CMB. Here, the Coma cluster or different galaxies, alpha is essentially a numerical factor, which describes an effective potential for the gravitational dynamics. So there's a different context there for dark matter.
So what you're saying is it could have smoothed out to create this constant effect that it has on galaxy clusters?
Our prevailing theory now is that galaxies are visible in certain wavelengths. And the visible wavelengths are as a result of stars that are shining. In the X-rays, you can also see galaxies. And the X-ray maps of galaxies are largely because of interstellar gas in a galaxy. So you're seeing two different snapshots. You're seeing a snapshot in the visual, which tells you where the stars are, you're seeing a snapshot on the X-ray, which tells you where interstellar gas is. Now, if you measure the movements of stars, you find that the velocities flatline. That induces us to come up with some model for why the rotation curve looks like this rather than falling precipitously. The model we've come up with is that galaxies, in addition to the visually seen matter, stars, and the gas, the X-rays, which were also observed, they contain dark matter, which we don't directly detect. We know that the mass density, the overall mass density of the universe, has to be a particular thing in order for the universe to be flat, which it approximately is. So we measure omega in matter to be 0.3. We measure omega in dark energy to be 0.7. So 0.3 plus 0.7 is approximately 1, so the universe is flat. Now, the 0.3 is broken up into two different components. One is dark matter, and one is ordinary baryonic matter, visible matter, things which we interact with. It turns out that the distribution is that omega dark matter is about 0.26, and omega visual is 0.04. Those sum up to 0.3. Now, what this means is that 4 out of 26 is roughly 1/6. This means that 80% of the matter in the universe can't be bothered to interact with you at all. It means that there's a lot of matter in the universe that we just don't detect except through its gravitational effects, like in these rotation currents. But this matter is very important for maintaining certain aspects of the universe we do observe, like its flatness. So we notice that there is this dark matter. We don't know what it is yet, but we also notice that in order for these rotation curves to make sense, this dark matter is distributed in a spherical halo around the galaxies. So that's the status of things today. Yeah?
First question, for the formula given to us for the mass density, in the denominator it's 4 pi RV r squared. So I know it says that RV is the variable radius, but then what's r squared then?
Which question are you looking at?
The first one, tutorial set.
Okay. So R is the distance, okay? RV is some canonical distance scale to which you're comparing things. So RV is sort of fixed, R is a physical distance. It's how far you are from the center of whatever you're measuring.
But then wouldn't our mass enclosed in that distance as well change?
Yes. The mass changes as a function of distance. M is a function of R.
Oh, okay, so MV is only associated with R and not R.
So RV is a parameter. M is a mass that's describing the amount of stuff within some radius. Yeah,
Do you have consultation times?
show up to my office. If I'm around and I'm not busy, I'll be happy to chat.
So what's your office number?
What?
What's your office number?
120. Other questions? Are we done? Okay, see you guys next week.
I guess for now, what I was having as like tutorials is sales-based marketing.
You don't need to.
Would you like to do more? So I guess maybe I'll just